start the search session on web attacks. We're actually starting with Kevin talking about your sensor is my sensor, weaponizing censorship infrastructure for availability attacks. If I'm talking, I'll just stop talking and hand over to Kevin.
Awesome. Thanks so much. Give me 1 sec to get my screen share going. All right, can everybody see this? You should get a thumbs up or a yes in the chat. Beautiful. And everyone can hear me? Fantastic. Alrighty. If at any point I stop being audible, just seriously cut me off, interrupt me, and let me know, and we'll try and fix it. I'm good to go whenever. I assume yes. Cool. Alrighty. Hey, everyone. My name is Kevin Bach. I'm from the University of Maryland. Before I get started, I do want to thank all the WOOT organizers, Mateus, Fang Fei, Eric, all the AE folks, everyone behind the scenes pulling this off. It's been a ton of work putting together the event, and I've really been enjoying it so far. And I also have to give a shout out to all the other collaborators in the project who aren't up here with me, because this really has been a team effort. So today I'm going to be talking about how attackers can weaponize a key feature of censorship infrastructure to affect availability attacks, and that feature is residual censorship. Before I get into that, though, let me give you a quick run through of what nation-state censorship looks like today and how residual censorship works. So let's say we have a user located inside some censoring regime, and they're trying to communicate with some resource outside the country, some website. And as the user makes requests, there is some censoring middle box that is performing deep packet inspection, or DPI, on those requests. And they're basically searching for any forbidden keywords or content. Now, as the user generates requests that the censor is okay with, these will bypass unaffected. But if the user generates something forbidden, in this case religion, the censor will then move to disrupt the connection, and this happens in different ways. A key feature, though, of many censorship systems is that they don't stop here. They also have something called residual censorship. And residual censorship is a feature by which the censor will continue to block all communication between these two hosts for some small period of time. This is almost a punitive form of censorship. So, for example, even if this user tries to make an innocuous request to the server, if residual censorship is active, the censor will still disrupt this until that residual censorship time has elapsed. Now, there are different types of residual censorship, though, and we can categorize these by how much information the censor remembers when it activates residual censorship. So, for example, when this client and server are talking, this is a source IP address and port communicating with the destination IP address and port. If the censor remembers all 4 of these pieces of information, the IP port, source and destination, we can call this 4-tuple residual censorship. If it remembers only the source IP address and the destination IP address and port, we call this 3-tuple residual censorship, and so on. What you'll notice is that the fewer pieces of information that the censor holds onto, the more aggressive this residual censorship is. With 4-tuple residual censorship, the client only needs to choose a new source port, and this happens by default, and then they'll be unaffected by this residual censorship. With something like 2-tuple residual censorship, though, the ports the client and server use don't matter. They'll be entirely cut off from one another once this is activated. In this talk, I'm going to show that this feature of censorship infrastructure can be weaponized. And it can be weaponized specifically to block any pair of hosts, innocent hosts, from communicating across the censor's borders, even if what they're communicating is completely innocuous. The idea of this attack is pretty straightforward, but the details get a little tricky. So I want to first give you the intuition for what this attack will look like, and then we'll get into the details of both how residual censorship works around the world today and what we need to pull this attack off. So to pull off this attack, we have some off-path attacker, and we'll assume ahead of time that the attacker already knows the IP addresses of the victim client and server that they're attacking. What the attacker will do is it will spoof their source IP address to be that of the client. And then it issues a forbidden request that crosses the censor's borders destined to the victim server. Of course, the censor sees this and assumes that the client just made this request to the server, and this then activates residual censorship within the censor between this client and server. What this means is that if the client now tries to make an innocuous request while this residual censorship time is still active, they will be unable to. The censor will step in and censor this, even though it's completely benign. So what this is showing is that attackers can restrict arbitrary benign communication from crossing censors' borders. The attack conceptually is simple, but like I said, the devil's in the details. And there's a few questions we need to answer to evaluate this attack. So for example, how long does residual censorship last in various places around the world? Are there limitations to what the sensor will block or process? Many sensors in the middle boxes are also stateful to TCP. They try to track the three-way handshake. How can we even trigger these sensors in a stateless manner? And then, arguably most importantly, how can we even test and evaluate this attack ethically? So for the rest of this talk, I'm going to split this into two sections to break down these questions. First, I'm going to present more details on the current state of residual censorship around the world. To study this, we obtained multiple vantage points within censoring regimes in Iran, China, and Kazakhstan. We find significant differences, actually, in how residual censorship systems are implemented, how long they last, when they take effect. All of these things impact the efficacy of the attack. Next, I'm going to speak to how we can go about weaponizing this feature. I'll show how we designed ethical experiments using a tool called SP3. This stands for a simple, practical, and safe packet spoofing protocol. And then we use this to launch this attack against ourselves, hosts we control, from over a dozen vantage points in different geographic locations around the world. So first, let's talk about what does residual censorship look like today. So first, we looked into what protocols are affected by residual censorship. Different countries censor different things. And so we started by testing these 6 protocols: HTTP, HTTPS with SNI, and going forward, for simplicity, I'm just going to refer to this as SNI. HTTPS with ESNI, or encrypted server name indication. I'm going to refer to this simply just as ESNI. DNS, SMTP, which is actually censored in China, and other, and I'll come back to this other in a moment. We find that not all protocols, even though they're censored by these countries, are actually affected by residual censorship in the first place. And actually, the mechanism by which residual censorship is implemented is not consistent between these countries. The Great Firewall of China, for example, injects resets for residual censorship, and they don't do this until after the three-way handshake completes. Whereas in Iran and Kazakhstan, they use null routing, or black holing, to affect residual censorship. This other here on this table, by the way, this refers to the Iranian protocol filter. Iran currently has a system running where if you use any protocol they don't permit on specific ports, regardless of the data you're trying to transfer, that connection is censored. So this other is literally a catch-all for any protocol that Iran does not approve of. We also find that the type of residual censorship is not consistent either between countries or even between protocols censored by each country. China, for example, has 3-tuple residual censorship for HTTP and HTTPS with SNI, but their ESNI censorship is actually now more complicated. It starts with 4-tuple residual censorship, but if you trigger it multiple times while 4-tuple is active, it then turns on 3-tuple residual censorship. It gets more aggressive the more you poke it. Iran and Kazakhstan, on the other hand, are purely 4-tuple residual censorship. And all of these things, again, will affect the efficacy of the attack. We next tested the duration of residual censorship. And this also varies both between countries and within each country. For example, in China, the ESNI residual censorship runs for somewhere between 120 and 180 seconds, whereas their HTTP censorship is only 90 seconds. In Iran, the difference is even more stark. The protocol filter, when it's active, only affects connections for 60 seconds, but its SNI censorship runs for a minimum of 180 seconds. And this asterisk here refers to that in some experiments, we saw it last even longer, up to 5 minutes or more. As we'll see shortly, the longer residual censorship lasts, the easier it is to weaponize for the attacker, the lower the cost is to pull off this attack. We also tested if residual censorship is bidirectional, if it affects traffic entering the country in the same way that it does traffic leaving the country. In general, we find this is true. Every protocol and system we tested, with the exception of the Iranian protocol filter, acted bidirectionally, both affected traffic and activated residual censorship in both directions. Importantly, though, we find that the sensor is still tracking the direction of traffic. So once residual censorship is triggered in one direction, it's only actually in effect for that one direction. So even though you can trigger censorship in either direction, the sensor knows which direction is the problematic one. So in summary, residual censorship is implemented differently around the world. There's different censorship mechanisms, resets, null routing, and others. Different types of censorship, even within countries. They act bidirectionally, but the direction still matters. Now that we have this info, in the second half of this talk, I'm going to discuss how we can use this to weaponize residual censorship. Before we get there, though, we need to ask a different question. We need to solve this question. how can we trigger these sensors in the first place? Every sensor I've discussed so far today is stateful. They try to track the state of the three-way handshake. So it shouldn't be enough just to be able to issue requests while spoofing your source IP address. This should not work. Fortunately, we actually ran into this problem in a work we ran concurrently to this one. And this will appear later this year in Usenix Security, where we found that middle boxes were also weaponizable to perform TCP reflected amplification attacks. In that work, we detailed how we were able to use a machine learning algorithm to search for ways to elicit responses from these middle boxes. And what we found was that middle boxes aren't actually doing a very good job tracking the state of three-way handshakes. And in fact, we could trigger these middle boxes without properly completing any three-way handshake. In total, we found 5 packet sequences that, when we put forbidden requests in them, trigger a large fraction of middle boxes around the world. For this paper, what we use is we can send a SYN packet followed by a pushback packet containing a forbidden request. And this sequence of packets is enough to successfully trigger residual censorship, even if these sensors are trying to properly track the state of the three-way handshake. Now that we have the ability to trigger sensors, we need to work on how we can ethically evaluate this attack. Our goal here is to be able to attack ourselves without affecting any other hosts. So we need the ability to spoof traffic, either to or from some censored regime. We want to do this specifically between hosts we control. We also need to have full control over the packets we send. So the mechanism we used for this was SP3. I'm going to walk you through our experiment setup. We have our client machine, server machine, and we use SP3 as the attacker. Now, a key feature of SP3 is that it requires the receiver of spoofed traffic to consent to receiving that spoofed traffic before SP3 will send it. So the experiment setup looks something like this. We have a server connects to SP3, and it consents to receiving the spoofed traffic. Next, we use SP3 to spoof the source address of the client, and then send a packet sequence containing a forbidden request, something the sensor forbids, to that server while pretending to be our client, which is located somewhere else. This should trigger the sensor and initiate residual censorship. Next, the client issues their own innocuous request to the server, and we can see if the sensor interfered with this connection. Now, recall that the direction of residual censorship matters, so the attacker needs to be on the same side of the sensor as the victim client. For these experiments, we use the public SP3 instance that's currently being run by the University of Washington, and that's outside censoring regimes. That means for our clients, we use test locations located geographically dispersed around the world and ran servers inside our censoring regimes to test this out. So to show you specifically what this looks like, this was our experiment setup. We had our attacker, SP3 in Washington. We had 16 total external vantage points scattered around the world, and these were our victim clients. And I know there aren't actually 16 black dots here. There were some vantage points that were either geolocated at the same location or within the same city. So they show up in the same spot on the graph. You can see the censoring nation states here in red and our location of servers within each of these censoring nation states here. So let's talk about our results. These are the results across all of the protocols we could trigger for every location to every other location. On the left, you can see all the victim locations we tested: Australia, China, India, Iran, Ireland, Japan, Kazakhstan, Russia, the UAE, and the USA. On the top, you can see the destination servers we tested. These were in Kazakhstan, in Iran, and in 2 different locations within China. So here are the results. First, you'll see that in some countries, the attack was highly reliable. For example, both protocols we tested in Iran and HTTPS in Kazakhstan worked with 100% reliability against every client we tested. The check marks in this table denote 100% reliability, X marks denote 0. You'll see Kazakhstan is interesting here, and it's not quite as consistent as Iran. And we actually found this strange result where the protocol we triggered censorship with mattered, more so than the location of the victim. If we trigger censorship with HTTP, we get different reliability for this attack than with HTTPS. We hypothesized in the paper that Kazakhstan has physically fewer HTTPS censoring middle boxes that our traffic is being load balanced across compared to HTTP, which they've been censoring for longer. On the flip side, you'll see that China is much less reliable. There are some victims for which we could reliably launch this attack, others against which the attack never worked, and still others in which the attack worked some of the time. For the next few minutes, I want to dig into why we think these failures occurred. So to get insights into why this attack failed, for the cases that it did, we developed the ability to run a source spoofed trace route. So we would have SP3 pretend to be our client and issue a traceroute, record the responses from the client, and then reissue that same traceroute from the client. By comparing the network paths they take and then running experiments to see how many hops away the sensor is, we can estimate at which points these paths converge to the server. What this shows us when we look at these traceroutes is that in many cases when we fail, the attacker's traffic would enter the country at a geographically different point than the victim clients. What means that what's happening here, what we believe, is that the attacker is successfully triggering residual censorship, but they've actually just triggered a different middle box entirely from the one that processed the victim's packets. This shows that this attack is actually partially limited by the location of the attacker geographically relative to that of the client. Next, I want to discuss what it takes to sustain this attack. So recall that residual censorship doesn't last that long. We talked earlier, it was really 3 to 5 minutes at the most. So how could an attack keep this going for longer? The answer to this question really depends on the type of residual censorship. But our goal here is to be able to block and prevent some client IP address from communicating with some server IP address and port. But the amount of work the attacker needs to do, again, depends on that type of residual censorship. Recall that in 4-tuple residual censorship, the sensor remembers the client's IP address and their source port. The problem is the attacker can't guess the client source port. It will be random every time. So in order to make 4-tuple residual censorship useful to the attacker, what the attacker has to do is simply retrigger censorship from all 65,535 source ports. Recall, though, that residual censorship only lasts for a certain amount of time. So can the attacker act fast enough to block all of these ports? We can calculate the speed required to keep this attack going indefinitely. And we can calculate this based on the size of the packet sequence required to trigger residual censorship, times 65,535 for all the ports we must send, divided by the duration that residual censorship lasts. To use Kazakhstan, for example, if we want to use HTTP residual censorship, it requires 145 bytes to trigger the censorship. This is a SYN packet followed by a pushback packet containing a forbidden HTTP query. And this lasts for 120 seconds. When you do this math out, this means the attacker only needs to hold a network speed of 634 kilobits per second. This is not very fast. With 3-tuple residual censorship, this actually gets even easier. With 3-tuple, the sensor doesn't remember the client source port at all. We don't need to play any of these games. All we need to do is trigger it once per duration that we want this to run, which means in China, if we want to do this for HTTP, the attacker just needs to be able to sustain 13 bits per second. And this shows that a weak attacker, a very weak attacker, can launch this attack and launch this attack effectively. But it actually gets worse than what I'm describing. And the reason for this is that some of the sensors we described, the victims can actually help sustain the attacks on themselves. We found that in both Iran and Kazakhstan, the residual censorship timer resets if the client issues an innocuous request or issues any network traffic while that timer is active. Any traffic that matches the rule resets the timer of the rule. What this means is that by default, as the victim's TCP stack is retransmitting data, that retransmissions are unknowingly sustaining the attack on themselves. We also asked the question, could the server detect this while the attacker is doing this? And the answer, unfortunately, is if the attacker is smart enough, no. The attacker can limit the TTL of the packets, the time to live, and they can set this up such that it reaches the sensor, but it will die before it reaches the server. So this is the type of attack that an attacker can launch, that the client will have no idea is ongoing, the server has no idea is ongoing, but can still operate successfully, even in very low bandwidth environments. There are some limitations to this attack, though. The attacker needs to have a vantage point. The vantage point needs to have no egress filtering. It needs to share a similar enough path with their victim. Their traffic needs to cross a sensor, and it needs to cross a sensor that has residual censorship. And they need the ability to trigger that sensor statelessly. Unfortunately, we found that there is a surprisingly high number of shared network paths. I mean, for example, in Kazakhstan, our attacker in the US could successfully affect traffic leaving Europe, Australia, Japan, all over the world, highly successfully. So this seems pretty bleak, but what can be done about this? There are some mitigations available to censorship infrastructure. They could abolish 3-tuple residual censorship, this more punitive form of censorship. They could upgrade their system such that null routing should track sequence numbers, so it doesn't just blindly eat all packets within a flow. They could update their systems to try and properly track the three-way handshake. Unfortunately, there aren't really any good countermeasures available to victims, because this is just baked into how these nation-state censors operate. Now, there are more details and results in the paper that I unfortunately don't have time to run through today. We did more experiments to examine what ports are affected in these various countries. We studied the reliability of residual censorship. We had more details on how to weaponize that strange ESNI case in China I mentioned. We also speculate and do some analysis on the true breadth of this attack. What other countries might be affected by this? But just in sum, censors can be weaponized to launch availability attacks. And it really doesn't take a very strong attacker to do it. Collectively, our results show that nation-state censors pose a much greater threat to the broader internet than was previously understood. To learn more, there's going to be more information about this attack and the other attack I mentioned earlier in this talk up on our website later today at censorship.ai. Thanks so much.
Awesome. Thanks, Kevin, for a great talk. We don't have too much time for questions. If there's a quick one, please go ahead and type it in, and I'll relay it, and I'll actually get started with one. How did you determine the forbidden content?
That's a great question. So the forbidden content, it can vary by country, but fortunately, there's all sorts of great tools out there that are designed to track and monitor which content each country forbids. So you can go to Uni, Citizen Lab, Censored Planet, and all of these tools are actively on a daily basis tracking what's censored in each of these places.
Okay. And maybe a very stupid question. You partially answer it, but I want to ask it anyway. How can you make sure that your messages are not being dropped by the fake packets that you send? They're not dropped by your provider or as part of because you're coming from a different ASN. Right, so
you're saying as the attacker, how can you make sure this attack is functioning? It's a little tricky actually from the attacker if you don't have access to either the client or the server. You can play some sort of games like inject traffic at the server that you know should give you a response. Like if you inject a SYN, hopefully you'll see a SYNAC, or that will go to the client. It can be tough to get insight as to whether your packets are going to where they need to be. So we tested this by just having control of one of those sides and then monitoring that the traffic actually got there.
Okay, is that a too strong assumption for the attacker, or is this realistic?
I think for these experiments, it's realistic, and I think for the broader context of the internet, this is realistic. As egress filtering starts to be rolled out more and more, it's getting more difficult for attackers to find these vantage points with unlimited egress filtering, but it's still unfortunately common. Like you still see these reflected DDoS attacks happening all the time, and we unfortunately have not yet solved the problem of egress filtering. So as much as I would love to tell you that no, it's not an issue, I don't think I can do that honestly just yet.
Right, cool. Thank you. There's a couple more questions on the chat. I would suggest that you take them and answer them from the chat. Thanks again for the talk. This was super interesting. I learned a lot. And we'll move on to the next talk